Hello, this is Carlos Perez-Delgado on behalf of the authors, presenting the video abstract for our paper titled Coherent Parallelization of Universal Classical Computation. We begin with a discussion of the existing literature. Higher order Hamiltonians are ones that have third degree and higher terms. While they do not seem to appear naturally, they can and have been engineered. Research into implementing higher order Hamiltonians in energy efficient ways is ongoing. What is well known is that they provide methods for improving both metrology and battery charging. The question we ask here is, are there any other applications? More specifically, can we obtain any advantage in computation? We are happy to be able to answer this question in the affirmative. Our main result, in a nutshell, is a method we're calling Coherent Parallelization, or CP for short, that can speed up any and all classical computations by a factor that is up to quadratic in the input size. This method acts much in the same way that parallel computation does, but using quantum effects. Hence, the name. Here is how it works. Suppose we want to perform two NOT or poly-sigma Z gates on two different qubits. We can perform each gate sequentially, that is, one after the other. That will take some time t. We can also perform the two gates in parallel. This doesn't reduce the actual cost of any individual gate, but because we're performing two gates in the same time that it would take to perform one, we say that we've reduced the amortized cost of each individual gate to t over 2. Coherent parallelization takes advantage of quantum effects to reduce the time cost even further, to 1/4 the sequential time cost. The careful observer will have two questions here. The first regards the energy. Clearly, a more energetic quantum system would have a speed advantage in performing a computation. Hence, in our axiomatic computational model, we upper bound the power, or energy per second, used by any computation at any point in time. This allows us to compare two different computations fairly. The second question is about universal computation. Implementing NOT gates is clearly not sufficient to build a universal computer. In our paper, however, we show that we can use coherent parallelization to speed up the implementation of a universal gate set for classical computation. So, what are the consequences of our result? Because coherent parallelization can be used to speed up any classical computation, the applications are literally endless. Here's a couple of concrete examples, however. Classically, we can sort a list of n arbitrary integers, sequentially in time n log n. This time is known to be optimal. If we use parallel computing, we can reduce the time to log n. Using coherent parallelization, we can reduce the time cost all the way down to constant time, regardless of the value or size of n. This example showcases the theoretical limits of coherent parallelization. Even if we have a fairly modest physical device, as an example, a coherent parallel register that can perform 3 gates coherently in parallel, we can speed up classical computations by a factor of 9 over standard sequential processors. As we increase the size of the quantum register, we increase the speedup by a factor that is quadratic in the size of the register. This brings us to our closing remarks. In its theoretical limits, CP provides a sizable advantage over classical sequential computation. But even a relatively modest-sized coherent parallel register of a few qubits provides a quantum advantage. This means that CP is not an all-or-nothing technology, but rather it can provide some degree of quantum advantage from early on in its development, with the degree of this advantage growing as the technology matures. This makes CP a naturally attractive technology to invest time and resources into. This is especially true since, given its universal nature, CP provides a motivating reason to eventually move all digital computation to quantum hardware. Thank you for your attention.